Hey guys, so today we want to transition from our discussion of the wave and particle theories of light back to our more ultimate goal of discussing the configuration of electrons within an atom. So first today we're going to look at Niels Bohr's work and the ultimate model of an atom which he described. So Niels Bohr was a Danish physicist. You'll find as your studies of science progress there are two major areas where the fields of physics and chemistry overlap. One is in quantum structure, or nuclear structure, or atomic structure, whatever you want to call it. And the other is in thermodynamics, which we'll discuss in the spring. So first let's talk about Bohr's experiment. Depending on how you're taking this class, we'll either do this experiment in class or we'll find some way to do a demo online, probably with a YouTube video that I find. But nonetheless, what Bohr did is he took a glass tube filled with first helium. So his initial experiments dealt with the atom of helium. So you can probably guess why helium is a good fit for any kind of experiment dealing with the structure of an atom, because it's the most simple atom. Okay, today we know it's the smallest, so it has the most simple structure. So he had this glass tube filled with helium, and then he had this electric current. Okay, and I apologize, my art skills aren't great here. Okay, but he ran an electric current through the glass tube full of helium, so a very high energy current, and light was emitted. Okay, so nothing super special about that. But what he found that was interesting here, and let's go back and review real quick. Let's put this on hold and think about what we discussed with white light or normal light in a prism. So we know when white light is shown into a prism, the light is bent twice and you see a rainbow. Okay, so you see the continuous spectrum. Okay, so you see every color, and there's no clear differentiation between the colors. Okay, we see every color with one smoothly flowing to the other. So when Niels Bohr took the light that was being emitted from the tube full of hydrogen and allowed it to pass through a prism, he saw what was called a line spectrum rather than a continuous spectrum. Okay, so we only saw very narrow bands of light, okay, at very specific places. And the actual line spectrum for hydrogen is in your notes there. I just kind of made one up here. So rather than seeing a continuous spectrum, he just saw the single individual lines. And this was very interesting to him. Okay, this kind of surprised him. Okay, he had expected to see a continuous spectrum. So given this information, he came up with this theory. He had this theory that, well, if we only see lines at very specific places, there has to be something that is creating light at these very specific energies. Okay? So now let's talk about two terms that we'll use to describe electrons. We have a ground state electron, so I'll abbreviate GS electron, and that's just an electron in its lowest energy location. So we discussed previously that the closer an electron is to the nucleus, the lower in energy it is. So a ground state electron is just an electron in its lowest energy location. So an excited electron isn't happy to be there, but an excited electron is just some electron that is higher in energy than its ground state. So yes, we're just saying higher in energy than its ground state. Okay, so it's somehow gained energy and has been promoted to a higher energy level. So what Bohr proposed, based on what he saw from the line spectrum, was that if you have an atom, okay, so we know we have the nucleus, Rutherford has already proven that. He said, well, if we have defined areas, and this is Bohr's theory again, if we have defined areas where electrons can be, okay, and they can only be in those well-defined orbits. If you have an electron in its ground state, in a low energy state, and it absorbs energy somehow, so in this case it absorbed energy from the electricity, and it gets promoted to the higher energy state, okay, when it falls back down, the energy has to be released. Okay, so this is the light that we see. So we'll just say that electrons absorb energy to be excited, and they emit energy here in the form of light when they fall back to the ground state. So when the electron falls back to its ground state, it emits some energy. Okay? So if electrons could be anywhere around a nucleus, then an electron might move from here to here when it's excited. But then it could really move back down to any lower location. So if it can move to any location, it can release light of any amount of energy. So we know that certain energies of light correspond to certain wavelengths, and certain wavelengths correspond to certain colors. So if there weren't any defined areas where electrons had to exist, we would see the continuous spectrum of light. Okay? But we didn't see that. We have the line spectrum. Okay? So Bohr said, well, if we have the line spectrum, there has to be defined areas that electrons can be, and we can correspond each of these lines on the line spectrum to a specific transition. So we call it transition when an electron moves to a higher energy level to a lower energy level, or lower to higher. So let's say we have, I'll just draw a separate hydrogen atom down here. We have 2 energy levels. And I'll draw that second dot as the electron there. I don't have another color, sorry. So we add energy. I'll just add energy. We excite the electron. Okay, so the electron moves to a higher energy level. I'll write as an E there. So here we have an excited atom. Or we'll just call it an excited electron. So if it's excited, it's at a higher energy level. So now the electron is going to go back to its ground state if it's no longer receiving that energy source. So it moves back to its ground state, energy, and we'll say energy in the form of light, is emitted. Okay. So that's kind of the process for producing one of these lines. So if I had, for example, an electron that started off in a different location and it got promoted to a different energy level and fell back to a different energy level, it would have a different line on the spectrum. So each different possible transition here corresponds to a different line on the spectrum. So it turns out the line emission spectrums are kind of like the fingerprints of atoms. So every atom has a very unique line emission spectrum because all atoms have unique numbers of electrons. They have unique properties about them. So this process of producing line emission spectrums was actually used to discover quite a few different elements. Okay? So they all produce different bands of light in different energies, and we can say energies are colors here because different energies produce different colors because they have different transitions possible based on the number of energy levels they have. So what Bohr said, based on all this information, was that every single atom, and whatever it might be, has these set locations where electrons have to be. So he knew that electrons weren't in a static location, they were orbiting the nucleus. But he said there's these tracks, if you will, that the electrons must travel on. And they can move from one track to another track, but they have to stay there. And we refer to this model as the Bohr model of the atom. So this is probably the model you're used to seeing, where you have the nice rings of electrons that we'll call energy levels, and the electrons reside in them. And when they absorb energy, they get excited, they move up. When they move back down, they release energy in the form of light, and they go back to their ground state. Okay, so this theory of electrons having defined locations where they have to be was how Bohr explained the line emission spectrum that he had. So a couple of terms that we use to describe these locations, we have an electron cloud. Okay, so an electron cloud is just the general area where electrons can be. So the term electron cloud would encapsulate all the different tracks, if you will, and that's not a scientific word, that's a word that I'm using, all the different locations where electrons can be fall within the electron cloud. Okay, so at any given time, an electron is going to be somewhere within the electron cloud. So then more specifically, we have the term orbit. And that was the term that was used to describe the specific rings or tracks the electron could be on. So we can say an electron is always within within the electron cloud, but it's always on a certain orbit too, and it can move from one orbit to another, and moving up and down is what caused the line emission spectrum. So we know to move up and down, they had to absorb just the perfect amount of energy. So there is a very certain amount of energy that causes an electron to jump from here to here, and a very precise amount of energy that causes an electron to jump from here to here. Therefore, when it goes back down, it releases that exact same amount of energy, and that's why we see the nice corresponding colors of light that we can perform calculations on to determine the energy change that created that transition. So we have a term that is quanta, Q-U-A-N-T-A. So a quanta of energy is the amount of energy needed for an electron to undergo a transition. Okay, so we call a quanta of energy, or we say a quanta of energy is what is necessary to promote an electron to a higher energy level. Or a quanta of energy is what is released when an electron moves from an excited state back down to its ground state. Okay, so this was Bohr's basic idea of the atom. So we still use the Bohr model in this level of chemistry class, and we'll discuss it quite a bit throughout the year. But we now know that Bohr's model, although it was very good and is still widely used, wasn't entirely accurate. So now we have what we refer to as the quantum model of electron configuration. So the quantum or the quantum mechanical model of electron configuration is very math intensive. So Bohr observed these line emission spectrums and created this model based on observations. The majority of the quantum mechanics model is mathematical in nature. So these models were creating using mathematical calculations that are far beyond the scope of this class, and to be honest, far beyond the scope of most college level chemistry classes. But one thing that is important to note about the quantum mechanical model is that it does not try to define the exact area of an electron. That's the key difference in the Bohr model and the quantum model. So the Bohr model, so we have these very defined areas where we can find an electron. So we now know that's not exactly true. What the quantum mechanical model does is it predicts the probability of finding an electron in a certain place. So we can do calculations to predict where an electron might be, and we can do calculations to predict the probability that we find it there. So in your notes you have some information typed out about some key scientists that contributed to this model. You have Heisenberg, Schrodinger, whose famous Schrodinger equation was the basis for a lot of the quantum mechanical model, and I believe de Broglie is also defined in your notes. I'll read through that, be aware that these men existed, but for the sake of this class you don't need to know a lot about the quantum mechanical model. Okay, so now we have an idea of the basic location that electrons can be, and we also have this idea that, well, based on the properties we've discussed, electrons have these properties of waves. Okay, they're releasing this light, this energy in the form of a wave. So at this point we can say, well, electrons somewhat behave as waves, but they're able to move from one location to another. Okay, so they're also kind of behaving as particles. And then the quantum model kind of takes it beyond that and gives a new description of electrons, which we won't really discuss. Okay, but now that we have this general idea that electrons are in orbits around the nucleus, what we want to do in the next few videos is dive in a little deeper and talk about how we can more specifically define where an electron is likely to be in relation to the nucleus, and how we can differentiate between different elements based on the location of their electrons.